In this video, we're going to cover section 4.7 on numerical integration. This is the last section in chapter 4. So in this section, we're going to learn how to solve problems using numerical integration, such as Riemann sums, like we talked about earlier, midpoint rule, trapezoid, and Simpson's rule. We have to revisit that method because in some situations, there is not a way of finding an antiderivative through a formula or through a substitution method or through an integration by parts. So we have to have a way sometimes of still evaluating and approximating. All right, so numerical integration is usually used in the following situations. First, when the antiderivative of the integrand may be difficult or impossible to determine directly. So if it can't be done by substitution, it can't be done by a formula, it can't be done by parts, or it's very, very complicated. Or you may have data that might not conveniently fit into a common function. So you might just have a bunch of numbers in a table that you have to create a graph for and then use a Riemann sum to approximate values because you don't actually have a function to work with. All right, so when we talked about Riemann sums before, let's kind of review how the setup worked. We want to approximate the definite integral from a to b of f of x dx. We took the interval from a to b and we divided it into n, or usually you will be given that value of n, like 4 or 8 or 6 or whatever, equal size subintervals. So we're going to write those out like this. So we're going to start at the beginning value here, a. So a over to the first subinterval endpoint x1, then from x1 to x2, then x2 to x3, all the way up to the n minus first, then ending at b, which would be the nth. This delta x, or the width of each of those, is the same as it was before. B minus a, the width of the whole thing, divided by how many pieces you're dividing it into, divided by n. All right, so we draw these rectangles. The rectangles are erected over each subinterval, and then you have a choice that you can define the height of each subinterval by using a left endpoint value of the interval, or you could use a right endpoint value, or you can pick some other value. So if you use a left endpoint for each subinterval, your heights would be, the first left endpoint would be your a, the beginning. So you find f of a, then f of x1, all the way up to the n minus first. This is how we did it back in the earlier section in this chapter. The area of each rectangle is the width, which is your delta x, multiplied by the heights, which are these numbers here, giving you the total area under these rectangles using left endpoint to be. We'll call it L for left endpoint subscript n, meaning how many pieces there are. The width times the height of the first rectangle, that's the area of rectangle 1. The width times the height of the second rectangle, that's the area of rectangle 2. Width times the height of the third, right, all the way to the end. This is the width times the height of the last rectangle. So the base is the width times the height to find area, and then we sum them all together. All right, you could choose the right endpoint of the subinterval to find the height. So remember we started at a, so the first right endpoint of that first little subinterval is the x1. So x1 is the height of rectangle 1 if you're using its right endpoint. This is the height of rectangle 2, the height of rectangle 3, and then at the end at b, that's the right endpoint of the last subinterval. So the right endpoint for n rectangles is the width times the height of the first, the width times the height of the second, the width times the height of the third, all the way down over to the end. All right, so often the average of these figures is calculated to give a better approximation. So usually you calculate your left endpoint approximation using left endpoints as heights, then you do it for the right endpoint, and then you average the two numbers together. All right, so let's try an example. Find the approximate value of the integral from 0 to 3 of the square root of e to the x plus 1 dx using 6 equally sized subintervals. Okay? All right, so first we're going to find the left endpoint approximation for 6 subintervals, in other words, L sub 6. So your subintervals for left endpoint, the a value is 0. That comes from here. So 0, we go to 0.5 here. We should have probably done this part first to show where these are coming from. So you want to find your delta x kind of probably your very first step here. So the 3 minus 0 is your b minus a divided by 6. We were given an n value of 6. So 3 over 6 is the 0.5. So you start at a, move over 0.5. That's your first subinterval. Then pick up where you left off at 0.5, move over another 0.5. So it's from 0.5 to 1 is the second. From 1 to 1.5 is the third. From 1.5 to 2 is the fourth. From 2 to 2.5 is the fifth. And from 2.5 to 3 is the sixth. So there's 6 little pieces. It's like dividing your x-axis up into those little sections. All right. So if we use left endpoint, it's kind of nice to organize this in a table. Your heights are given by this column. So they've written down the subinterval that we just saw in the previous slide, 0 to 0.5, 0.5 to 1, etc. So they highlighted here in red all of the left endpoints, right? So they're using these left endpoint values for this column. Your width was the 0.5, that was the delta x value. So plugging in your left endpoint into the function, our function was this, e to the square root of e to the x plus 1. Plug in the left endpoint into that same function, plug in this left endpoint, plug in this left endpoint, all the way through, all get plugged into here. Calculator gives me these numbers. So then your area, width 0.5 times height. Width times height equals width times height, all the way through. Okay, I would suggest setting up tables like this to organize your work because there's a lot of calculations going on in these problems. All right, so you identify your subinterval, or I would find delta x first, that's your width column. Identify what the subintervals look like based on the a and the b value for the beginning and end. Decide if you're using left or right. So if I'm using left, we pick those numbers to find our heights by plugging into the function. Calculator gives me these numbers, multiply width times height to get our areas. And then we simply add them together. So all these numbers over here added together is where this 6.91925 is coming from. This last column, these numbers added up, gives me the total. Okay. All right, now we're going to find the approximation if we were to use the right endpoint. Same function. Okay, so our delta x is the same. Our intervals look the same. Our width is always still the same. However, when we choose to plug into the function to find the heights, we're going to choose the right endpoint of each of these. So that's why this time they're highlighted in red for the right endpoint. So the first height is going to be plugging in 0.5, then plugging in 1, then 1.5, 2, 2.5, and 3. So plugging those right endpoints into the function f, this thing, right here, calculator evaluates to these numbers. So again, the width was the 0.5 times the height from here is the area of the first rectangle. Width times the height, area of the second rectangle. Width times the height, all the way down. So these are all the areas using the right endpoint to find height. And then adding up all these numbers again, 8.5081. Okay. And then if they say find an average, I think in my math lab on those problems, you'll be asked to do a left and a right for the same problem. All right, then you're going to average those numbers together to get the average. They didn't do that on this slide here, but that's going to be asked in the homework. All right, you could also have chosen to use the midpoint of each subinterval to calculate the height of the rectangle. Okay, and this is a formula that kind of would generate your midpoints, but it's probably easier to kind of use your table method and identify separately each endpoint and just plug it in rather than trying to utilize this formula to find it. So if your interval is from a to b and you're dividing it into n equal pieces, again, your delta x is b minus a over n. So the approximate value of using the midpoint of each subinterval to find the height, we'll call it m sub n, is your delta x. So a plus x1 divided by 2 is the midpoint of subinterval 1, so plugging that into f. This is the midpoint of the second subinterval, the midpoint of the third, all the way to the end. But like I said, it's easier, I think, just to draw out your number line or your table for whatever problem you have, identify your intervals, and just write down what the midpoints would be. Okay, so same function that we just did the L and the R for, same value for N, we're going to do a midpoint approximation this time. All right, so that first subinterval, remember B minus A is 3 minus 0, which is 3 over 6, or a half. So starting off with the A value, which is 0, moving over a half, is the first subinterval. The midpoint of that subinterval, so between the x values of 0 and 0.5, the middle is 0.25. The second subinterval goes from 0.5 to 1. Its middle point is 0.75, and so on. So I would just go through and write down all the midpoint values of each of those spaces. Okay, so here again is the table. These are the subintervals for that problem. Our widths of all of those are 0.5. So the 0.25, the 0.75, and then between 1 and 1.5, the midpoint is 1.25. Between 1.5 and 2, the midpoint is 1.75. Between 2 and 2.5, the midpoint is 2.25. And between 2.5 and 3, the midpoint is 2.75. If it helps to draw it out like this, at least on a number line, to just see it, you can. So you find each midpoint separately, just like before. Plug the midpoints this time into your function. Use your calculator to evaluate. Multiply the width times the height to get the area for each of those different subintervals. Okay, then add them all together. So the sum of the areas in the last column we would call M sub 6, totals to be 7.6564. That's slightly better approximation of your definite integral than the L or the R, because if you notice in the picture, each rectangle, right, is hitting the function where there's some above and some below. So it's kind of more of a balance. So all of those answers are different approximations of the area under the curve. Okay. This is a function that does not have an antiderivative. We can't find it by any method, so the best we can do is an approximation. All right, we also have another, so that those three, L, R, and M, are using left, middle, and right, are using what we call rectangle approximations. Riemann sums using a rectangle. Okay, we have another option of using a trapezoid. Okay, so if we create trapezoids instead of rectangles, we can add the areas of each trapezoid together, right, to get a different approximated value. So again, our interval is from A to B. We're going to subdivide it into n equally sized subintervals, so our delta x is found the same way, b minus a over n. The approximate value then of that, given by what we call the trapezoid rule, is just a different formula. So the trapezoid rule for n rectangles, or n subintervals, I should say, delta x is the width. We find f of a and we divide it by 2. Then we just find f of x1, f of x2, all the way up to the one right before the end. Plug those numbers into your function. And then we add on the endpoint f of b divided by 2. So the f of a and the f of b are divided by 2. Otherwise, you're just adding up all these numbers in the middle, finding that sum, and multiplying it by your delta x. Okay, so let's try this. So we're going to take that same problem again with n equals 6. So from the previous example, we had calculated f of 0 before. In other words, just plug 0 into the function, because that was a, right? Our subinterval endpoints were 0.5, 1, 1.5, right? We already figured those out. So we're plugging all of those into our function all the way to the end. So plug in each subinterval endpoint, 0, 0.5, 1, 1.5, 2, 2.5, and 3. Get those numbers. So your trapezoid rule says delta x, which was 0.5, they've just written it as a half, but that first number out here is your delta x. It's f of a over 2, right? That was this number you divide by 2. Then you add on this number, then this number, then this one, then this one, then this one. All those just get added in the middle. And then again at the end, you take the f of b, which was your f of 3, and you divide it by 2. So the first and the last are divided by 2. Everything else is not. You're just adding them all up. And then your calculator evaluates. 7.714. All right, and then our last option on a numerical method is called Simpson's rule. Okay, it's similar to trapezoid rule, but in other words, you're still going to find your delta x the same way, b minus a over n, that never changes. If you're using Simpson's rule, in the front you have your delta x, which is b minus a over n, but there's also a 3 on the bottom. All right, so it's the delta x times a third basically out here. So here we're just going to have our f of a at the beginning and our f of b at the end. And those numbers that we had before in the middle, this time the coefficients of them alternate 4, 2, 4, 2 all the way through. So you just, the f of a and the f of b are just coefficients of 1 by themselves. So you start with f of a, and then you have 4 in front of f of x1, then a 2 in front of the f of x2, then a 4, then a 2, then a 4, then a 2, then a 4 eventually, and then finally an f of b. Okay, so the same problem again, this time using Simpson's rule. All right, so again, we have our f of 0, our f of 0.5. We've already found our subinterval endpoints from the previous problems we've done. So we know what those are, plugging in the 0, the 0.5, the 1 into our function. B minus a over 3n. Remember, we needed that in the Simpson's rule formula. So b minus a is 3 minus 0. N was 6. So the bottom is 3 times 6. So 3 over 18, or a sixth. All right. So we've got our 1/6 in the front. That's our f of a, or f of 0. Then remember, it's 4 times this one, plus 2 times this one, plus 4 times the next number, plus 2 times the next number, plus 4 times the next, and then finally our f of b. You always start with a 4, and if you've done this right, you should always end with a 4, excluding the f of a and the f of b. Those are always beginning and end. But if you start in the middle after that f of a, you start with a coefficient of 4 and go 4, 2, 4, 2, 4, you'll end on a 4 before the f of b. Okay? All right, and then we add all that up, we get 7.67565. So if you compare the answers from L6, R6, M6, T6, and S6, they're all roughly the same, right? Not exactly, some are better than others, but they're all in the general vicinity of being a similar value. So they all represent different approximations of that definite integral. All right, so our summary here, the process of numerically approximating the value of a definite integral using geometry is called numerical integration. Right? We always start by dividing our interval up into n equal pieces, beginning at a and ending at b, where the width of each subinterval is b minus a divided by n, b and a being the endpoints of your integral. Okay, they just run through a summary here of the left endpoint formula, using the right endpoint formula, the midpoint rule, although this formula itself isn't necessarily all that helpful. Those are the ones where you just want to write down each midpoint and plug in and organize your information in a table. Trapezoid rule formula, Simpson's rule formula. Okay. It explains a little bit up here where the Simpson's rule is derived from. It's using pieces of parabolas. You don't have to know that stuff, but that's kind of where this formula is generated. All right. So I would recommend writing all those down or printing out this last few pieces of the PDF that's posted in Blackboard for this PowerPoint and having those handy when you're doing the homework. There's not very many problems assigned in this section because they do get time consuming, but you should, I think there's there's assigned one with left, one with right. Then you'll do an average, one with midpoint, one with trapezoid, and one with Simpson. Okay? All right, so that is the end of 4.7, and that concludes the end of chapter 4.